Hello, this is the final report for the Many-Core Programming project. My name is Hergus and I'm reporting for Group 8, composed by two students, Srboljub Stepanovic and Hergus Reja. I will start with an introduction of the project requirements and of the application these requirements apply. This project aimed to create a parallel version of a determinate application. The application we are going to work with is called PuzzleDiff. It is built to find similarities between two pictures or between one picture and a set of pictures in a given set. In order to better prepare the parallelization of this application, we need to have a better understanding of the algorithm behind the PuzzleDiff application. So let's go through the steps that compose this algorithm. It starts with basically the conversion of the picture into black and white or grayscale format, followed by the process of the division of the picture into a grid of blocks, which in this case is a grid composed by 9 rows and 9 columns. For each block, the gray label is computed, it's calculated from the pixel, and then it's stored. An array of 8 elements that represent the correlation of each block with its neighbor, then it's computed and it's constructed. In the next step, the concatenation of these arrays form the signature of the picture. At the end, the normalized distance between the signatures of the pictures is computed, which will be used as the main attribute for deciding about the similarity of the pictures. The main requirement of this project is to make a parallel version of this application using a parallel language called Silk+. The work starts by analyzing the sequential version of the application. As a first step in the analysis, here we show the call graph of the main function with the presentation of the most important function in the application. Here we can see some of these functions like puzzle field cvec from file, puzzle vector normalized distance, puzzle field dvec from file, and many other important functions that are used inside PuzzleDiff application. But to have a better understanding of how the algorithm is executed, we can show the control flow of the main function, which is executed in the original version with two pictures given as arguments. Here we can learn more about the order in which the functions are called and the control flow of the application. Here the control flow is divided in two parts because for showing purposes. In this way we get a deeper understanding of the application. In order to have information about the most time-consuming function, we will next proceed with the profiling of the sequential version of the application using different scenarios. The first scenario is comparing two images with respective sizes of 0.5 megapixel and 2 megapixel. We show a top-down approach of the functions and their CPU time needed. As a hotspot here we notice the GD image getTrueColorPixel function, which consumes most of the time. Profiling is done with Intel VTune amplifier. And we can notice here that even puzzle field average light gray late scale function consumes some time, actually 10 milliseconds. Next, the second scenario, we compare medium-sized pictures, 2 megapixel and 5 megapixel. On this scenario, we can notice again GDImage getTrueColorPixel that is used in the function that converts the image from color to grayscale. And then we notice here a new function, which is Puzzle Auto Crop View, which we'll talk later on. In the scenario, we have our profiling information with Puzzle Auto Crop View as the first function, noticed from the time consumed. And then we have GDImage getTrueColorPixel. Here we show the two most time-consuming functions, and with these results we come to a conclusion that in order to have a more efficient execution of the application, we need to speed up the execution of the above-mentioned functions. So here is one point of focus for the parallelization process. I mentioned the comparison of a pair of pictures. Now we need to focus on the scenario of comparing one picture with a set of other pictures. Here comes the need of making our solution scalably efficient. Our notion of scalability is defined in three levels: in picture size, in number of pictures, and in number of processing elements available in the architecture in which will be executed. We'll go through these levels one at a time. We have picture size. Scalability in this dimension is defined by the ability of the application to scale with the increasing number of picture size. The main goal is to create a parallel version that scales well with the increasing size of the picture. In order to do so, we should be able to improve the execution time of the functions used mostly in bigger picture sizes by parallelizing them appropriately. The next level of scalability concerns the number of pictures that the application will process. The modified version should scale well with the increasing number of pictures in the directory. In order to do so, we need to parallelize the process of calculation of picture signatures. We aim to have as much parallelism as possible in here, and even a longer portion of parallel region. The third level of parallelism is the number of processing elements. Our solution will expose as much parallelization as possible here, since the runtime system takes care of the scheduling and mapping of the parallel strands of the application, or the threads. Our solution has the focus not in only performance with a specified architecture, but mainly on the scalability level. Next, I want to mention the phases of our application engineering process. Like mentioned above, the requirement is to create a parallel version of the application with focus mainly on the scalability. Next, on the design phase, we have to create the architecture of our solution, where the structure is defined mainly from the sequential version. Based on the profiling we did before, we decided to parallelize the following library function, or what we call the inner parallelization. We decided to parallelize Puzzle Auto Crop View since it was related to most of the time consumed by the application running on bigger picture sizes. We decided to parallelize function Puzzle Get View from GDImage, as even this function was among the hotspots in the application. We thought it would be better to parallelize puzzle fill average light gray light scale function, and at the end we thought of parallelizing puzzle vector sub, which basically computes the distance between two picture signature. Next, in the design process, we created a new file called find similar picture that is responsible of the parallel process of the calculation of distances of the pictures in the directory from the reference picture. This we call the outer parallelization. In this function, or in the modification of the main function, we define the 10 most similar picture found in the picture set, and also the 10 most identical pictures found in the picture set compared to a reference one. Here we show a control flow of the modified main function. Actually, it's a conceptual control flow. So you can notice from the portion of the right side of the control flow, we insert a loop in yellow, which logically will do the process of calculating the distance and then storing the picture according to the distance in two different vectors. But as we will see from below, we will miss something in here. We have the coding step, or the coding phase of our process. Here we show the codes of our modified function, as we mentioned above. We begin with puzzle autocrop view. Here we mainly use Silk4 for the loop parallelization process. Next we have puzzle get view from GD image. Again, we see the usage of the Silk 4, and we proceed with puzzle fill average light gray light scale, and end with the puzzle vector, does, as I said before, the subtractions of the signature or calculates the distance between two signatures from the picture. Next we have the modified version of the main function. We used parallelization for computing the distances of the picture from the picture of reference. So this is the only parallel part in the main function. Differently from what we thought before, we ended up with a solution like this in coding, mainly to avoid races inside the main function. So we only calculate distances in parallel by using Silk4. Next, we proceed with the sequential part of the main, in which we basically divide the pictures in three groups based on their distances. We have three vectors of pictures that are identical or that have distance 0, are identical or close that have the distance less than 0.12 from the reference, and pictures that are close resemblance or have a distance above 0.12. At the end of the main function, we do the sorting of the vectors according to the d value, and then we print the results in two formats selected that are able to be selected by the command line. By the arguments, we print the results in the standard output, or we print the results in the file name. The name is given in the arguments. We test our solution by executing the application, giving two different arguments. First, we select the display as the output. As we can notice here, the output is divided into regions. The first region with pictures that are similar to the referring picture, that are sorted by the d-value, and the second region with pictures that are identical or closely resemblant to the reference. Next, at the end, we even print the execution time of the application. In the second way of executing our application, we selected as an output a file named results.pictext. Here we can find what the file looks like after the execution with a small picture set. Now it's time for comparison in the execution time of the puzzle diff up before and after the parallelization. It's clear from the profiling analysis that the reduction of the execution time for the function defined as hotspots in the sequential version. Here we can notice the reduction of GDImage, getRecallPixel, or puzzle autocrop view and puzzle fill average light gray light scale. Next, we should expose our parallelization strategy, which is based, as I said before, on two levels of parallelization, inner and outer parallelization. The inner parallelization is defined by the parallelization of the library functions, such as puzzle autocrop view, puzzle get view from GDImage, fill average light gray light scale, and puzzle vector sub. And as the outer parallelism, we define the modification inside the main in order to calculate in parallel the distances of the pictures from the reference one. By implementing this strategy, we benefit on the increasing of the number of pictures computed in parallel and on decreasing the elapsed time for the most computation-intensive functions that were defined by. We used SilkView as the tool for analyzing the parallelism inside our solution. And here we can show the results of parallelism factor, which for the whole program is defined by the level of 33, and for the parallel region by the level of 65. The benchmarking session on the Xeon machine of our parallelized solution, we got the following results of execution time. We did two groups of tests with medium picture set and with large picture set. First, we did the execution on the spinning disk, the normal hard disk. As we can see, there is quite a noticeable speed up compared to the sequential version. In the medium picture set, we had 250 seconds of computation, and in large picture set, we had 2,100 approximately seconds of execution. Next, we repeated the same process for medium picture set and large picture set, but on SSD solid state drives. Here we have in large picture set a more fast solution with approximately 1,600 seconds spent on comparing one picture with pictures in large picture set. As we can notice here, interestingly, the difference from the HDD becomes huge in the large picture set only, but in the medium picture set we don't notice such a big difference. Next, from the results we get from Hardware Info 64 program, we plot the CPU utilization during the tests. First, we show from the SSD. First, we measured utilization in SSD. As we can see from the graph, both CPU are equally loaded during the application execution to 100% most of the time, which shows a potential for further performance with more computational units. Then we proceeded with the same plot, but on HDD or spinning disk. The total peak utilization of both CPUs is below 100% with large oscillation. That tells us that in this case the application performance is not bound by the number of cores but from the I/O performance. So in theory, if we would have more cores to add to the execution, we will have a worse timing in this case. Results compared to our initial plan, we had been able to parallelize the application by decreasing the execution time with a factor of 6.5, as it showed by the measurement done in the Xeon machine. Scalability regarding the number of pictures, as noticed, suffers a small decrease when we compare improvement factors of medium picture set with large picture set, with the last being in the level of 6.25. We think this result comes as a logical conclusion of the picture being heterogeneous in the large picture set, with the 98% of the picture being in the region from 10 megapixel to 0.5 megapixel. Scalability in the picture size was not tested properly in this case because errors were reported while attempting to read big picture size. Further improvement suggestions. One reasonable suggestion would of course be to improve better library function in order to be able to explore scalability with big picture. A more detailed comparison of the picture would give better accuracy of the application, but with further costs in computation and memory usage. And dividing picture into groups based on their distance from the reference could be done in parallel using reducers, as was initially our first strategy. Further improved based on the testing results. Testing showed a good scalability from our solution in terms of parallel factor. The level of scalability in the number of pictures was not so satisfying, since the increased number of pictures we noticed a slight decrease in the speedup. Testing with even larger set of images and a detailed analysis of application could give us a more scalable solution. What we will be doing differently next time, if we had the opportunity to redo this project, we'll try to use more from the potential of C++ programming language with reducers, arrays, and probably exploiting SIMD instruction more. Make more testing while developing our solution, and have a more formal process of re-engineering the sequential version of the application would help probably in reducing the time effort needed. And at the end, as a conclusion, we would like to present some points. We got a better understanding of the notions of parallelism and scalability, very much needed in today's architecture. We developed a good knowledge of C++ language and their feature and possibilities. We had the opportunity to do some reverse engineering process on the application with the purpose of deriving a parallel version from the algorithm. And as a final suggestion, generally a two-person group it's not advisable for this kind of project. Thank you very much for the attention.